Hello everyone, welcome back to our YouTube channel, Becoming a ROS Developer. My name is Rodrigo, and today we have one of our students who has completed the course ROS Basics in 5 days, Janka, and she's going to be showing us a real robot project that you can do at the end of this project, and you actually implement on a real robot. So hello, Janka, how are you?
Hi, I'm good, thank you.
Awesome. So yes, whenever you want, you could please start sharing your screen and show us what you've done with your project.
Yes, can you see my screen?
Yes, we can see the robot and your terminal.
Perfect. Then I will just launch my program and keep my fingers crossed that it works. So in the beginning, the robot's supposed to find the wall, so it's spinning until it detects that the wall is in front. So that seems to be going well. So we're in step 2 now. So then it's moving closer to the wall. And in step 3, it's supposed to turn until the wall is on the right side so that it can start the actual lab. Right, and now we see the robot starting the lab. I have to say my robot is not the fastest, so it might actually take a while until it finishes
No, that's
the
okay.
lab. But yeah, in testing it did work the last time I tried, so let's hope it works today as well. And then we can see the robot tells us what it's doing. So if it's going forward or turning away or towards the wall. And then once a second, we're getting feedback about the distance that it has traveled. So we're seeing, how far the robot has gone and what it's doing.
Right.
So this corner is the most difficult. So let's hope it makes it through this one.
Why do you think it's the most difficult?
I'm not sure. I mean, they should all be the same, but in testing, this is the only corner where it has ever gotten stuck. So I'm not sure why.
Okay.
But
And what do you mean by getting stuck? It just can't move forward or keep spinning, or does
it
it
drove
crash?
into the wall a few times, but not recently. So I think maybe that's something. I think I've fixed that. So because it seems to be.
I think
Seems
if
to
the
be
sun
working.
is hitting directly, sometimes that makes a difference, right?
Oh, that's
Because the
interesting.
LiDAR won't return correctly.
Right.
Okay, so it looks pretty good.
Yeah.
And so we can see that the feedback, I'm assuming that's from an action, is telling us that it's moved 3.5 meters.
Yes.
And will this robot stop when it completes lap or keep going and return something? What is it going to do?
It's supposed to stop, and
Okay.
it's also supposed to return a list of all the positions that it's been at during the lab. So I'm testing whether I'm saving the first position where it started after it found the wall. And then I'm checking if it's close by that position again. And that should theoretically make it stop and then also return the list of position where it's been at during the lab. So I guess it started somewhere here in the front. So that should happen quite soon. Yes, so there we are.
There it is, yeah.
I'm gonna stop here. Yeah, so when we see, it says that it's done. And then before that is the list of all the positions that it went through during its lab.
So that's the path that it took.
Yes, exactly.
Okay, awesome. That was great. That was worked at the first try. So if you can just explain to us how you've done each part of each section of this road. Great. I can see your presentation now.
Yes. So yeah, this is just a quick explanation of what I've done. So I'll go through what each of the tasks were and then how I solved them. So the first task, like throughout the project, the first thing I learned was how to make the robot follow the wall. So in this part of the project, the robot is supposed to move forward and keep a 30 centimeter distance to the right side. And then it's also supposed to turn at the corners. And the way that we were supposed to solve this is using topics. So the robot, in the main code, it has a subscriber that subscribes to the laser scan topic. So that has the information of like how far away things are all around the robot. And then in the code, we read out the laser values for the front and the right side of the robot. And then there's the logic for steering, like should we go further to the wall, further away, or turn at the corner? And then the publisher publishes a twist information to the robot, so that makes it actually move. This is what my code looks like for that. So the subscriber is just listening to the laser forward and the laser on the right side. And then the logic is like if it's if it gets too close to wall in the front, it turns at a corner, so there's no forward velocity but just spinning. And then then I'm checking whether it's in between 30, if it's more than 30 centimeters or less than 20 centimeters, it moves either towards the wall or away from the wall. And then if none of these apply, it just goes forward. And the most important thing I learned in this part of the project is that I need to make the robot stop once in a while, because otherwise it will just go crazy. So it's important to actually let the robot read its sensor values before sending it on movements.
Okay.
And then the first time I tried it, it actually looked like this. So I confidently steered the robot into the wall, because I didn't realize that the laser sensor is different in the simulation and in the real robot. So that was something I learned, which was very valuable. Moving on to the next part of the project. So in the next part, we were supposed to find the wall. So the robot is supposed to identify the closest wall and then turn towards it and then move forward until it's at a 30-centimeter distance to the wall. And then once it has moved forward, it turns to the right side so that the robot is ready to start the wall following behavior. We're doing this using services. So in the main code, we're sending a request to the find the wall service, which also subscribes to the laser scan topic in the same way that the main code does. And then we determine which laser position is the closest to the wall, and then turn and move forward and then turn again. And throughout this whole movement, this whole calculations, the publisher has a twist value again that it sends to the robot so that it actually moves. And then when the wall is found, we're sending a response to know that the service is finished. And this is what it looks like. So we're just sending the request in the main code. And then this is what the wall finding actually looks like. So we're checking whether the forward one is close enough to the minimum so this is the minimum of all the laser values, and then the laser forward has to be like roughly like a very short margin, because if I had it exact, it sometimes overshot. So this is like good enough to the closest. And then in the first step, we're turning until the front is the closest. In then step 2, we're just moving forward until it is 30 centimeters away. And once that is finished, there's step 3, where we turn until the wall is on the right side of the robot. And then we stop and send the response back. Okay. The final part of the project is the odometry recording. So in this part, we store the robot's position at each time step. And then we also give feedback on the distance that the robot has traveled. And when the lap has finished, so when the robot has done a full round, we return the list of the positions where the robot has been. And we do this with actions. So here we send the goal to the odometry action server, and the action server subscribes to the odom topic, so it gets the values about the position of the robot. Then in the code, we record and store each position, and then also we provide feedback already while it is still running. So this is different from the services, because the actions can actually provide feedback while they run. We also compare the position, the latest position, with the initial position to see if the lap has finished. And then when the lap is finished, we return the list of the odometry positions where the robot has been. And this so the calling the odometry is just the same as we learned it in the unit, so I haven't made any big changes here. And the subscriber looks like this. So we're just getting the X and Y position of the odometry, because we're moving in 2D. So the X and Y is what we want to record. And then this is the actual odometry code. So first we check if the robot has started moving, and if it has not, we're saving the very first value, which is what we need in the last step to check if the lap has finished. And we also append the position where it is to this odom record list. So this is what we also send back in the very end. Then while the lap is not finished, we calculate the distance that the robot has moved. So that's with the function down here. And add that, and then we send this as feedback. And this is what we can read out while the robot is running. So it shows us how many meters it has moved already. And then we also check if the robot has reached the starting point already by comparing this first value that we saved up here to the latest value where the robot is right now. And once the lab has finished, we're sending back the results as like the result list and stopping the robot. I just want to say some quick take-home messages that are not fully content related, but things that I personally learned during the course. So I didn't realize how different real robots and simulation robots were. So it's important to check the sensor readings in order to not run your robot into the wall. Also, something I lost a lot of time on was spelling. So at some point during the actions, like my action server was working with odom record, but I was sending the goal to record odom. And that took me a long time to figure out. And also just to like use a lot of time for testing, because there's more things to test than you think. But yeah, overall, I really enjoyed the course and I learned a lot. So I just want to say, yeah, thanks for listening.
Right. Thank you. Yes. Thank you, Janka. Very nice presentation.
Thank you.
Really clear. Like the images and how simple the information is. So congratulations.
Thank you.
Have a couple. I have a main question here.
Yes.
And I think it's interesting. So you mentioned that an important thing you figured out was that you had to send a stop message in all your conditions once you were doing the movement. And I saw a lot of sleeps, correct?
Yeah.
And so a sleep and then a stop. Okay. So why do you think that is? Because you said otherwise the robot goes crazy. What do you mean by, first, what do you mean by crazy? And then why do you think that is that you need to include this?
Yeah, so I think, so this is actually something where I got so stuck that I posted on the forum about it and I got actually really important, like it was really helpful. So I think the forum is a great place to ask questions. I just think that my robot was, whenever there was none of the conditions, it just went anywhere. And I think I also had it too fast. I think that was also part of the problem, that I had the speed set too high. So it went into the wall, or it went and like took down all the decorations in the robot area. So I think maybe I overdid it in the end. Maybe it's stopping too often now. But I think I should not move it faster than the laser callback gets new information. And since I need the laser information to update what the next step should be. So I think it's good to actually wait for the laser to realize where the robot is and then make the decision of where to move next.
Right. You're definitely on the right track. So my question, you talked about the speed of the robot, but I'm also thinking that this behavior, first, it happened more on the real robot, correct? Than on the simulation?
I think so, yes.
Yeah. So the reason for this, my thinking, is the rate at which your node is spinning. It's not the velocity of the robot, but the rate at which your node, your follower, your wall follower, is actually spinning. So a couple of things on that. First is you did you add callback groups and re-entrant callback groups and multi-threaded executors in order for the callbacks not to step on each other. Yeah, okay. That's good then. And is there a rate that you specified? Sometimes you can do a RCL pi dot rate or a sleep on your function or something like that we can maybe look at that could give us a clue?
I don't think I did that. That sounds like a very smart thing to do.
Okay, yeah. So in here, if we go to the right, it's spinning. Also, you only need 2 threads here, I'm pretty sure.
Oh, okay.
One for your laser callback and one for your one for your laser callback, one for the the rest of callbacks you might have. And so at this point, you can actually tell the node how fast you want it to spin. So my guess is that what was happening while it was running into things is that you were trying to do too many things. I also saw sleeps on the callback functions.
Yes.
For the odometry, I remember the odometry.
Yes.
So that's actually a problem in terms of the data you're receiving, right? Because
okay.
every time the laser spins or the motors send out a message of the odometry topic or the laser or anything that requires a callback, so that callback is executed when a new message comes in, right? And these messages come in at a certain rate. Let's say odometry is quick. You know, it comes in really, really quick. And every time that happens, this callback will get executed. So if you have a sleep in there, then that means when the next message arrives for your odometry, it might still be in the sleep, right? So that program might still be sleeping, so you miss that next reading because the frequency is high. And all of that compounding it might turn into, your robot is basically with its eyes closed, and that's why it kind of runs into the wall until it can catch up and all the sleeps are back up and, it can kind of find itself. And it seems that you found a kind of balance where, you stop, you check, and then you move. That's why we saw it move, stop, move, stop. But I think that's the reason why you were saying, it's going crazy. You have to find out a way at which what's running is checking at the correct rate, and avoid sleeps as much as you can. Well, you should avoid sleeps in callbacks, especially for this reason. So I think that is the reason why you were running into those issues. But you found a really good solution, which was just taking it slow, and your logic was, check your lidar, move a little bit, and stop, and then redo it.
Thanks. That's really good to know. Thanks. I'll change it in the future.
Yeah. So that's the only thing I noticed. Other than that, it's a really nice project. Really straightforward and understandable. So I just want to congratulate you again, Janka, and yeah, good job.
Thank you very much.
All right. Cool. So let me here go back to my face instead of your screen. There we go. So yes, guys, this is what you can do when you take our course for ROS 2 or ROS Basics. We also have navigation and other courses that offer a certificate if you actually present your project with us, like Janka did here. So I invite everyone to do what Janka did here. And that's it, guys. We'll keep an eye out for the next presentations. And thank you very much, Janka, again for presenting this with us.
Thanks.
All right, guys, that's it for us. So we'll see you guys for the next presentation here at Becoming Your ROS Developer. Bye-bye, guys.
Do I need to do anything else, or is it?
No, we are done.